One of the rarely used pieces of equipment in my lab is a good old Simpson 260 VOM or multimeter. I'm not really sure which series this one is offhand. I think it's one of the later ones, but still not brand new by any stretch of the imagination. Oh, it's a tiny printing, but I think it's a Series 8, so a Simpson 260 Series 8. Very venerable meter. This is the kind I first used in a high school electronics class, probably back in 1975-ish, or somewhere around that point in time. And more recently, I was given, a friend gave me, another Simpson 260. Wish I could get rid of this glare. This is the original Simpson 260, the one that started the whole series. And this type of Simpson 260, which is usually known as the 260-1, some people call it the Series 1, but apparently the series designation doesn't really apply to this meter, that's something that came out later. It's just the Simpson 261 or original 260. They didn't really change the look of the meter very much over the time, and the dimensions are pretty much the same as the later models. And I'll do a comparison on that later on in this video. But I thought I'd do my usual documentary approach to this. The original 260 like this originated in the 1930s sometime. I haven't been able to find a definitive date, or year anyway. And they made it for quite a while. They were still advertising it apparently as late as 1946. I don't know if that just means that there was a lot of them made and they were still in stock, so still available, or if they were actually manufacturing them into 1946. One of the big differences is that there's no fuse protection on this at all, and also no calibrations. The later models added fuse protection and some calibration trim pots. On this one, you're just at the mercy of the component tolerances. Also, all the later ones, or almost all the later ones, had kind of an engraved, the graphics were, I don't know if they were molded into the Bakelite or plastic or whatever this is, and then filled with a little paint or something, which is a very high quality way to do it because it doesn't wear off. On here, even though it looks pretty, all these graphics are just silk screened on the front. And the problem with a lot of these is if they got a lot of wear, all those graphics would be just worn off by the action of the fingers being so close to the front panel. Also, because of its age, I think this model predated the use of banana plugs. I don't know if they didn't exist then, or if they just weren't in common use, or if Simpson just didn't like using them. I'm not sure, but they use the pin jacks. So even though the housings of each jack are the same diameter, the actual plug that plugs in is much smaller, and they look like this. Luckily, they're just still available from companies such as Pomona, so I could make up my own set of test leads to go with this meter. Anyway, otherwise it's really the same kind of thing. It has basically 3 controls like all Simpson 260s. It has a 0 ohms control. It has a like an AC/DC selector switch, and then a combination function and range switch. And contrast that with this later 260, you can see the 0 ohms adjust on the right side and the AC/DC switch on the left. And these later models added a DC minus, DC plus instead of just a simple DC. And certain later models also added an off position that you would turn this to. I think the main thing that did is it increased the damping on the meter movement for protection when it was in transit. Probably just shorted out the meter movement, but I haven't looked at the schematic. This meter had no such thing. And otherwise, really, it's a classic, and you can see how this influenced the evolution of the 260, because all the parts are in place here, really. So what I have here are two AA size Duracell Pro cells for low drain devices. I think these are intended for long-term backup and things like that, not things that draw a lot of juice. But according to the Batteries Plus store who made these packs up for me, they said these things were considered to be a lot more reliable when it comes to things like leakage. And they're made in the USA. So anyway, I've got a block of wood in there to separate them to get the requisite width, matching these original battery packs. These use size A instead of AA, and they have a bit larger diameter, I think. And these are potted and everything, but I've made these up to be the same height pretty much, so they'll fit into the clips. The length is a little shorter, which is fine. You can use the extra space. And Batteries Plus is welded on the jumper from a plus to minus at one end, and then welded on these little solder tabs. I had to buy the whole box. It wasn't something they usually carried. And the same thing with the C cells. Here's how one of the battery packs fits into a clip on the meter. And here's the other one on the other side. I've got it in there a little bit crooked at the moment, but they do fit. Okay, here's the insides, the guts. We have the two AA cells there and two more AA cells there. That is to get 6 volts, and then there's this C cell which gives another 1.5 volts. And I imagine those get added together for the high ohms range, so you'd get 7.5 volts excitation for that. It looks like most, if not all, of the range resistors are all carbon comp types instead of wire wound, and they're all on this phenolic board attached to solder mounting tabs. This is not a circuit board, it's just a phenolic base to hold all the tabs that they're soldered onto, and everything's done by hard wiring. And these little guys are wire wound resistors of some kind, just a bobbin with resistance wire, insulated resistance wire wound on it. And this is a, it says 1 microfarad. I'm not sure that's correct. I think it's probably 0.1 microfarad, 600 volts. And that would be for the DC blocking function that's used. Let's see here, I don't want to bust anything inadvertently. When the switch is in the output mode next to the AC mode, it would put that capacitor in series with the AC input so that any DC component would be blocked. And that can be handy for reading voltages in between sections of an amplifier, for example, where the AC signal you want to measure is riding on a DC carrier or DC offset. So then we have this single deck rotary switch here, and that is for the DC AC output selection. And there's a bunch of, they still look like carbon comp resistors stuck inside of insulating heat tolerant tubes, and I expect those are for the higher voltages. And there are the insides of the 4 jacks, and then there's the big selector switch, which just has all the wires coming off of it, which then go through the wire harnesses and to the various resistors and things. There's a couple of more, well, 4 more of those wire wound resistors of the kind that's just an insulated resistance wire wrapped around something non-conductive. And then you can see the reflection in there. That's the back of the meter movement, and that's, I think, all that's back in there. A few more internal details. I think I forgot to mention this little piece right down here with the 3 fine green wires coming out of it. That's the rectifier block. There should be 2 metallic diodes in there, so I think most likely selenium, but I'm not positive. There's other types of metallic diodes from that period that might have been used, but I want to say selenium's probably the one. So this bobbin resistor here would be the one that's in series with the common, in other words, the junction between the cathode of one diode and the anode of the other. This is where the incoming signal passes through. It comes up on this black wire, goes through this guy, and then goes into the diode. And then this one here is, this bobbin resistor is a shunt, which gets put across the meter movement, the coil of the meter movement, when you're in AC volts mode. And the positive of the diode comes out one side to the resistor, and the negative of the rectifier comes out and goes to this resistor. So the positive lead of the rectifier assembly comes and goes to this side of the bobbin resistor, and the negative side of the rectifier comes out and goes to this side. And then these 2 wires here ultimately make their way across the coil of the meter movement to act as the shunt. But of course they get switched into it. It's not always connected to the meter. And these 4 wire wound, but again it's insulated resistance wire. This is a 1 ohm, this is a 4 ohm, and this is a 45 ohm. And these are all 3 current shunt resistors in the ammeter part of the circuit. But this one here is not part of that, and I believe this is the lowest resistor, about 11.5 ohms, which is the common resistor used in the ohms ranges. All the other resistances are much higher and are handled by some of these other resistors up here, but these really low value resistors are handled with a wire wound approach. And I also want to amplify or clarify these resistors here. Originally I thought they were probably big wire wound resistors, but on closer inspection they appear to be just carbon comp resistors. And these tubes that they're in span the entire width. They go from one side to the other. So these are the two jacks for the 5,000 volt ranges. Let's see, this one's the AC 5,000 volt jack, and this is the DC 5,000 volt jack. And each of them goes into well, on this one it goes into the end, and it looks like the ends of two stacks of resistors are stuck together there, but the wire itself goes past that. And the same thing, the black wire goes into that sleeve. And then around on the other side, I can't really see what's going on in there, but I think what's in these things is just a whole bunch of carbon comp resistors wired in series and then folded over and going back in the other direction, and maybe part of a third pass going the other direction to make up the diameter. So instead of some big high voltage resistors, they just have a whole bunch of fairly pedestrian resistors wired in series. And then finally these exit out the other side with these two reddish wires, and they make their way to that single terminal on the switch right there, and then that red and green wire jumpers over and goes to this jack, which is the normal plus input jack. So all of those come together at that point. So that's the common of the first stage, or I'm sorry, that's not the common of the first stage, that's the common of the AC DC output selector switch. Well, here's the printed out prototype version of the label. Now I have to go see if it'll actually fit the battery pack. I think my recovery in Photoshop, I wasn't trying to make it look too good, but definitely better than the source material. Okay, I've upsized the label for a little better wraparound coverage, and I made a PDF of it and printed the PDF, but it came out smaller for some reason. I don't much care for that. Huh. I have to check the printing specifications here. Is it? It's on fit. I need to change it to actual size. Okay, let's see here. Here's the original. Yep, that's more like it. I think that should work. I'm going to put the PDF file up on my file share website along with the schematic of the meter in case anybody else wants to use these. Okay, it went on perfectly. Looks about as good as I could expect. Just held on there with a couple bits of Scotch tape. I could have glued it on, but I may want to reuse these labels at some point. I don't know. Tape seemed like the better option. Okay, there they are. And there's the other label that I made for the C cell. I doctored up a photo of one of the ever-ready D cells from about 1947, and the style matched the other ones, so I used that and then just took it apart in Photoshop and made it so it would work on a C-size cell. I think it came out pretty well. Okay, I've created a sort of a faux Burgess 422 label. I couldn't find any images of the historical battery other than that the 422 was this basic type, and I've got it wrapped around the ever-ready equivalent. So, but this label is not intended for vintage batteries, and these are these are single A cells in here, 2 of them. Their diameter and their length is larger, but the dimensions are such that they would wrap around modern double A cells, and the length would be about right. So here's a modern double A cell. And you can trim the top and bottom of the label to fit your specific cells. And if you want the battery that you get to fit the battery holders inside the Simpson 260, you need to space, and assuming you're using double A cells to make it, you need to space them out with something, because they won't be wide enough this way if you just put 2 of them touching each other. You need to space them out a little bit to get the necessary outer dimension. But I think that'll work out pretty well. It looks good. I think it looks reasonably authentic. I don't know what the shield here would have had besides 422 on it. I decided to put 3 volts on there, and I know from some other old Burgess labels of this vintage that they usually said something like, you know, A battery or something on them. So I thought that was reasonable to say that this battery pack would have 2 A batteries or 2 A cells inside the battery. So that's my story, and I'm sticking with it. Alright, and I've labored to complete the series. I have here a rough clone of a Burgess Unicell number 1 C cell. So I think it came out looking pretty good. Proportions are slightly off. The original would have had more space between the top of the shield and the black band, and the same on the bottom. Not much more, but a little bit more. But if I crunched it much more to make it fit better, then the width would get off or it would look distorted. So I went with shorter bands at the top and bottom of the shield. I had to recreate most of these little details in here, because while they were so fuzzy on the picture, I could kind of make out what they were supposed to look like. I had the original I worked from was so bad that I had to pretty much pixel by pixel edit this thing, and I had to try to fix the Burgess here. It was really rough, and I came pretty close to getting it looking right. The G looks a little fat to me, but it's the best I could do. And then all the other things were just in a simpler sans serif font, so I just put those in new. I wiped them out, replaced them with red, and then put them in as actual text objects. And this little thing down here where it says Burgess Battery Company something or another, this is super low resolution, just a few bits per character. The funny thing is it's almost impossible to read what the letters are on the screen, but when you print it out you can kind of see what it's supposed to say. And because that's in a particular font, I can't replicate that. So I left it the way it is. It's pretty small text. I did put in the Made in USA down there, which is, I think, the smallest font that the software that generates this can do. It won't allow me to go with a lower setting. It's like a 2-point or a 3-point or something. Pretty small, but it's legible. I made it with the top and bottom black bands a little wide, so it could fit slightly different makes of batteries, and then you can just trim it to the proper length. And I got the black lines so they came out pretty good when wrapped around. It's hard to see where the seam is. I'm pleased with it. This is about a day's work. Alright, so I'm set on the 2.5 volt range, and the red leads in the positive jack and the black leads in the negative jack. My meter is more or less zeroed, and I'm going to give it 1 volt. So we're right here. This is 1 here, so it's just a little bit on the left. I should mention that during my restoration of this meter, I found that the window had dropped down on the top side, even though some sort of clip was holding it up against the bezel on the bottom, but on the top it had gone down. It didn't seem like it was actually quite hitting the meter. The meter still moved, but I was concerned that it might hit the meter. It certainly didn't look good. So I had it had a lot of crud on it. I had a lot of trouble cleaning it up. And then finally I was trying to pull the glass forward and can't really get a grip on it. I ended up clamping the top edge right here in my bench vise in my shop, and using the big shop vac with its nozzle stuck onto the glass, I could pull it forward. And since the meter was upside down when I was doing that, I was able to just drip in some super glue all along the top and around the corners and hit it with a puff of accelerant, and that seems to be holding it, although I don't know how strongly, so I'm being very gentle with it. Anyway, okay, let's go to 2 volts. Again, it's a bit shy of 2 volts. This is almost certainly due to drift of those carbon composition resistors. Let's go to the 10 volt range. And now I'm on the bottom scale. So this is 2 volts here, and again it's just a little low. Go to 3, bit low, 4, low, 5, 6. Seems like it's getting a little lower as it goes up. Yeah, that should be 8. I think it's just always getting a slightly smaller fraction of current through the meter movement than it should. Again, due to the resistors getting out of tolerance. But it is working otherwise. That should be 10 volts, so it's that much short of full scale. Let's go to 50 volts. Now I'm reading on the upper set of numbers, so again it's a little bit shy of 10 volts there. As we noticed on the other ranges, it's closer to being accurate when it's to the left, and as we go upscale it gets progressively lower further away from the proper part of the scale. So let's go to 15 volts, and it should be here. Go to 20 volts, getting a little bit lower. 30 volts, yeah, progressively lower, so not accurate anymore. But it is working otherwise. Okay, I've switched over to the 10 milliamp range and function. The leads are still in the same place. I'm still on the DC position. My bench power supply is set for 24 volts, and I have it wired in series with my 4 to 20 milliamp loop tester, so I can get some reasonably accurate control of the milliamps. And I'm going to turn the supply on. I get my red indication. With the knob turned fully counterclockwise, I should be getting 4 milliamps. Since this is a 10 milliamp scale, this would be 4, so it's reading, again, just a little bit shy of 4. And up around here should be 10, according to the knob. Looks like it's pretty good, but I can fiddle the knob to get it to read that. If it was actually 4 milliamps, I think it'd be reading a bit short of that full scale position. Now let's go up to the, boy, it's hard to see that, isn't it? The 100 milliamp. Again, it has MA, capital MA, as if it was mega amp. Okay, so now we're on the 100, so everything's divided by that, and this should be 10 milliamps here, so it's kind of close. Let's turn the knob up to about midpoint, which should be 12 milliamps. And we're doing pretty well there. This would be 10, this would be 20, so it's on the first division out of 5, so it's reading 12 milliamps pretty accurately. Let me turn the knob all the way up, and it's just shy of the 20 milliamp position. So certainly the milliamps is working. And this range here, where it says 100 mic A, I'm sure that's for microamps, 100 microamps. I can't dial my tester down that far, so I'm going to take it on faith that that's working. Okay, I've switched over to the 250 volt position, and I've turned this knob to the AC position, which is really hard to see. There we go. And I've got the test leads still in the normal positions. The only other ones are for the 5,000 volt range, AC and DC, so we're not getting anywhere near using those. I have the test leads jumpered over to my AC access panel. Gotta get these out of the way a little bit. And I have my Variac hooked up to the AC access panel. So I'm going to turn that on. And we are in the 250 volt range AC, so we're using this red scale here. So 100 volts would be here, 50 volts would be here. Let's crank the Variac up. That's about 50 volts on the Variac, and it's reading just about exactly 50 volts on here. Let's go up to 100 volts, and right again, just about exactly on 100 volts, and the Variac will go up to 140 volts, and that's just about exactly where it is. So I would say that this meter is working really well in the AC volts department, which further suggests that the problem with the meter reading low was some resistors out of tolerance. And there's almost certainly different resistors for the DC volts attenuator compared to the AC volts attenuator. So that would be where the issue would be. Just for yucks, there's a lot of damping on the meter. Let's take it down to the 50 volt range. So we're reading the scale under the red line. It should be somewhere in the area of 25 volts, and it looks like it's right on the money. And that's just about where I know the the Variac says it thinks 50 volts is according to its scale, which is always slightly low. So I have to bump it up a little bit to actually get 50 volts. And it's just about right. So the AC mode is working very well on here. Okay, with this switch back in the DC position, I put the meter in the R×1 mode, and I'm reading up near full scale. So I'm going to have to adjust this pot and see if I can bring it in. Yeah, the pot's a little noisy, as one might expect from the age of the equipment. Anyway, so I've got it zeroed out, and it's connected to my Heathkit Decade resistance box, so I should be able to get some direct readings. The ohm scale is this top one here, so that would be 1 volt, or 1 ohm, 2 ohm, 3, 4, 5 ohms. Let's see what we get. That's 1 ohm, 2 ohms, 3 ohms, 4 ohms, 5 ohms, 6, 7, 8, 9. Let me go up to the next range and go to 10. Looks like it's pretty much right on the money. Let's crank in the units range and take it up to 5. Right on it just about. Let's go to 20. Ever so slightly low. Let me just see if this thing has drifted at all. Yeah, it has slightly. Let me re-zero it. Okay, I'll go back to 20 ohms, and it's right on. 30, 40, 50, 60, 70, and then of course it gets progressively inaccurate as we go towards the higher numbers. So let's go to the next range. I'll switch up to the R×100, and I always have to re-zero after changing ranges because different resistors are in there, but it looks pretty good. So I'm going to go up to 100 ohms here, and it's right on the money. 500 ohms. Let's go to 1K, and it's right on the 10. 20K, 30K, 40K, 50K. It's doing pretty well. Okay, I'm going to go up to the R×10,000 or 10K position. This engages the extra batteries, and I've got it zeroed in. So let's remember that a reading of 1 on here would be 10K. So let me go up to 10K, and it's right on the money. 2K, or 20K rather. Yeah, went from 10K to 20K. 30K, 40K, 50K. Let's go back and check 0. Sometimes they drift a little bit. Looks like it's ever so slightly high. Yeah, let's try it again. Go up to about 30K, 40K, 50K. Pretty accurate. Reading slightly high. Let's go up to 100K. And it's just a little bit shy of the 10 position, which would give me 100K on this scale. 20, 30, 40. So pretty good. I think the resistor that defines this particular range isn't as tight as the other ones, but it is working and it's doing pretty well. So the ohms range works on all of those ranges. There's the beauty shot. I'm struggling with a couple of light sources to try to minimize glare and not wash out any one part of it. So there is a more modern Simpson 260 on the right, along with the 260-1 on the left. About the same size. The newer one is slightly bigger, and a little deeper this way, and a little taller. It's I think slightly bigger in all dimensions. Actually, the width is just about identical, so the newer ones are slightly taller and a bit deeper. The meter size isn't that much different, but it's kind of interesting that the markings for the ohms range on here are just about identical between the two. The way they did it, in other words, the way they graphed out the scale. This one measures dB from -20 up to +10, where this one is -12 up to +3. And there's also an extra range on the new one for a clamp-on ammeter accessory. So that's just the comparison between the two. This knob here, the AC/DC output knob, is comparable to this knob here, which has AC volts, DC minus and plus, and an off position, which I believe shorts out the meter for better damping while you're carrying it around or transporting it. And then the 0 ohms knob is identical to the 0 ohms on here. This one's 500 milliamps, 100 milliamps, 10 milliamps, 100 microamps. This one is 500 milliamps. It still uses a capital M for milli. 100, 10, and 1 MA. So they're using a capital M for both micro and milli, which is, or I'm sorry, maybe not. I bet that's just 1 milliamp. So a bit different there on the lowest amperage scale. It has R times 1 times 100 times 10,000, just like this one does. And then we have 500 or 2.5 volts, 10 volts, 50 volts, or this one's 25 volts, this one's 50 volts. Then this one goes up to 50, this one goes up to 250, and then you can get up to 1,000 using the highest position here, whereas this one has an extra voltage range. But this one has a larger number of extra jacks. You've got this one to this one, that's across your shunt, just like this one has the plus and minus 10 amp jacks. I'm sure there's a shunt going right across there. Then there's an output jack here, which this one does not have. And then there's a plus 1 volt range, and then a 500 volt AC or DC jack, and a 1000 volt AC or DC jack. So this one's a little more convenient to use in that regard. But really, you can see the same inspiration. Well, if this was a Heathkit video, I would be talking about the manual. And of course, this is a pre-assembled product, not a kit, so it doesn't have the large assembly manual. And all we really have is a document, which is apparently originally a Simpson document. It covers both their Model 215 and the Model 260 AC DC volt ohm milliammeter. So maybe that's defense of the VOM. I was always taught that VOM meant volt ohm meter, but I know that it's often used to mean volt ohm milliammeter. Unless you're talking about like the AVO meters from England, where the AVO means amps, volts, and ohms. Anyway, so really you have a 2-page manual here. Not much to it. I got this off of the Simpson 260 Simpson.com website, along with the original Simpson schematic that I showed, or that I am showing in this video. So there's a general bit about it. The design is really identical between the 215 and the 260. It's just some small differences in the ranges, but otherwise they're essentially the same thing. So they say it offers the serviceman a small, compact, and complete instrument with high sensitivity for testing and locating trouble on all types of circuits. The large 4 1/2 inch meter provides a long scale that is easy to read, and the compact arrangement of the control units allows the overall size of the Bakelite housing to be comparatively small for maximum portability. The electrical circuit is designed to give maximum insurance against inaccuracy and damage to the component parts. Impregnated cable wiring is used throughout. The high-grade copper oxide rectifier, well, there's an identification of what type of rectifier it is, for AC measurements is individually calibrated with a precision wire bound. I wondered if they meant wound. Anyway, wire bound or wound shunt and multiplier. That suggests that possibly they were measuring each one of them in the factory and then making custom wire wound or wire bound shunts for the rectifier to match those characteristics. I don't think it would change very much, but it would assure the best accuracy. Glad we don't have to do that kind of stuff anymore. And then it says all metallized resistors are matched in pairs to close tolerance for accuracy and are firmly held in place by a special Bakelite plate machine for this purpose. I don't really know what they mean by this, what they mean by metallized resistors and matched pairs. There aren't any two resistors in here that have the same value, so I'm not really sure what they're talking about. Then it gets into the instructions, talks how to use the meter to measure DC volts and the various ranges. AC volts, the same thing. Then it talks out how to use the output meter, so you make the connections as for measuring AC volts in 3, AC volts in 3, except place the AC or the DC-AC output switch in the output position. A condenser, meaning capacitor, is connected in series with this switch for blocking out the DC component when connections are made directly at the plate. And that is where that designation you see on so many old VOMs, when they have either a jack or a switch position or both that says output, and you think, output, how does the meter output anything? What they're meaning is that when you're measuring the output of an amplifier stage in a tube circuit, that it's likely to be an AC signal riding on a DC offset. And so when you're measuring the output of an amplifier stage using tubes, you put the switch in the output position so that it'll strip out the DC component and just measure the AC part. That's the idea, and that's why they have that weird designation on so many old meters. Then it talks about the DC milliammeter, and then the ohms function, and then using the meter to measure decibels, and then finally it gives brand specific information. It recommends using a Burgess number 1 unicell of 1.5 volts, which we would just call a C battery, or a C cell more accurately today, and 2 Burgess number 422 batteries of 3 volts each, which is something that I'm talking about elsewhere in this video, that these days you can't get those, and those were made out of two A size cells, which are now a size that you don't find anymore. So those can be replaced by a pair of double A cells, forming a 3-volt battery, and then you have two of those batteries. So they point out when you can no longer zero the meter will be sagging to the left, and that's time to change the battery. If you're using only the lower ranges, you'd change only the C cell. If it's just the R times 10K range that it's sagging on, then you need to replace really both of those batteries. So just because this manual applies to both the Model 215 and the 260, and because the schematics look almost identical when given a brief perusal, I'm just going to point out a couple things about the two versions in case anybody gets confused by them. First off, even though the circuit design is identical between the two models, meaning the layout of the schematic is the same, the meter movement in the two models is quite different in its sensitivity. In other words, how many microamps need to go through it to get a full-scale reading. The 215 uses a less sensitive movement, requiring 200 microamps, I believe, to get a full-scale reading, while the 260 uses a 50 microamp meter movement. And that necessitates changing pretty much all the resistor values used for scaling in order to get the appropriate amount of current through the meter movement for any of the given ranges. So again, the circuit design is the same in terms of its layout, but the component values are pretty much all different. If one does the math on them, they still work out. You just have to bear in mind the 200 microamp meter movement on the 215. Then in addition, there are two ranges which are different: the lowest current range and the highest resistance range. So on the 215, the lowest current range is 250 microamps, while on the 260-1, the lowest is 100 microamps. And then on the 215, the highest resistance range is R times 1000. On the 260-1, it's R times 10K. Okay, let's take a look at the schematic for the 260-1. Apparently, Simpson had their own number for this. I don't know if this is just a drawing number or if it's supposed to be like an internal Simpson number for the popular face of the thing, 260. So WD 260. I don't know what the WD means. Anyway, this drawing originated in April 16th, I think, of 1940. And since the 260-1 originated earlier than that, this apparently wasn't the first drawing that was made for this model. And the interesting thing is that even though this was made closer to the end of the time when they made this model, it has quite a few errors in it. So, pretty simple circuit, a little hard to figure out because of the way it's drawn. But some things are pretty obvious. The AC and DC jacks for the 5000 volts, the plus and minus jacks for everything else. And here's your AC-DC output switch. They kind of jam the capacitor in there. And the way they've drawn this, these arrows here are supposed to be the wipers on the switch, so they can point at this, or this position, this, or this. And then the rotary switch is all laid out here in 4 wafers, or 4 decks, first, second, third, and fourth, with the rotor wipers all along the edge here. It's pretty easy to figure it out. All of these letters that are put next to most components, and I know that's supposed to be a W, but it looks like an upside down M. Weird drafting techniques here. Anyways, there's this table of component values up at the top, and that's what these letters correspond with, so you can figure out which values they are. And the positions of the switch are indicated along here. Now here, for microamps, they use mic A, and then capital M's for micro, or for milli. Small capital M's are used for milli instead of small m's. And let's see, what else is there? There's the rectifier. It's drawn more pictorially than schematically. I'm not sure why they would have done it that way. It almost looks like it's math symbols, right? But this actually represents the letter X, which is the letter key to the table here for rectifier. But if you just looked at it casually, you'd think it's plus times minus. And then, interestingly, they identify the meter movement as model 29. They have plus and minus for the 6-volt battery, but they don't tell you what the voltage is. You're just supposed to know. And then this one over here has no identification whatsoever and no polarity markings. I guess that you're supposed to know the big plate is positive, but if you're supposed to know that, then why show it here again? I would have failed my junior high school drafting class if I'd made a drawing as bad as this. Anyway, since this is a little hard to figure out, and because my biggest gripe with it is that a lot of the values, all the ones identified with asterisks here, so the potentiometer and 1, 2, 3, 4, 5, 6, 7 resistors have the wrong values. The numbers on almost all of them are correct, but the units are wrong. There's a lot of them that are marked as M for mega ohm, and in fact they're kiloohms. That's a big difference. And then this one that's identified as a 4050 resistor is 4950. First I thought it's just a sloppily drawn 9. It's like, no, I think they intended to draw a 0, but maybe the draftsman was working off of a sketch and somebody didn't make a very well formed 9. That's all I can think of. Anyway, if one does the math on the circuit, a 4050 would not work where a 4950 does. And then finally I took physical measurements of the 2 wire wound resistors associated with the rectifier. And all of these corrections I put on my own version of the schematic. There it is. So I tried to cram as much information as I could into the schematic. And I want to mention one thing, depending on where you look, but I think the most common identifier for this version of the Simpson 260 is 260-1. But other places say that it should be called the Simpson 260 Series 1. But then, for example, the Simpson260.com website says that the Series 1 designator didn't actually come into use until a later version of the meter, so I'm not really sure about the Series 1 part, except because it's so often called that, I put it here along with the 260-1. And of course in the day they would have called this a VOM, which suggests volts ohms meter, although some places would say that's short for volts ohms milliamps. I'm calling it by that name and also by the more modern name, multimeter. Anyway, so the whole thing is drawn in AutoCAD, and I just tried to get a layout that was slightly less cramped and easier to follow, and using more modern symbology. although I don't like using little rectangles for resistors. I always show them this way. It's the more classic way of doing it. Anyway, the switch for the AC/DC ohms is drawn more conventionally, and the rotary switches are shown as rotary switches. And let's see, I added the information that if you're measuring 5,000 volts, you have to be in the 1,000 volt position of the switch, even though you're going to use these jacks up here. I drew the potentiometer correctly and indicated the clockwise rotation, and that one side of it is not connected. In the original schematic, it's shown as a rheostat instead of a potentiometer. The batteries are shown more consistently with their voltage and what type they are, and with the plus symbols. All the information from the original schematic about the meter is on it. The rectifier is drawn more conventionally. I think that's about it, other than just fixing the component values to what I found out they actually are. I have my usual series of notes about conventions used for resistors, resistance values, and wattages. I describe what the component or part number identification letters are and how they're used. I talk about that the original 2 battery packs used in here, not counting the C cell, used a pair of A cells, which are now obsolete and you probably can't find them anywhere. And that these days it's more common to use AA cells, so I put a note in there about that. I have a historical note about the significance of this meter. I have a note about the incorrect component values on the original schematic, identifying which ones were incorrect and what the problem was. I have a note about how to use the 5,000 volts ranges, so it's almost like a little part of an instruction manual there. I talk about the fact that the original schematic and apparently Simpson didn't have any identification for the various parts of the switch, like naming the various decks or gangs or wafers, so I've left them unidentified too. I didn't make up a designation for them. And the position, the position terminals normally would have numbers on them, you know, number 1, 2, 3, 4, 5 or something. And Simpson didn't show that, so I don't either. So, and a note that if somebody's working on a 260-1, since Simpson chose to make all of the resistors, with the exception of just a handful, using carbon composition type resistors, that those things will drift over time, and there's no calibration on this meter, so unless you want to replace all the resistors, you're left with whatever accuracy you have with drifted resistors. Now, as the demo in my video shows, it's pretty good in my case, and maybe that's normal. Maybe most of them age that gracefully. I don't know. Then I have a 2-paragraph description. A common problem with these is that somebody will have removed the original batteries, both battery packs and the single C cell, and just left the wires hanging in space. And while they are color-coded, if mine is any indication, the colors have faded so much you can't tell what they're supposed to be. Simpson260.com has a method for going by the colors, but again, if you can't tell what the colors are, then you're stuck. So I took a more analytical approach and described how, with a continuity checker and a voltmeter, one can easily ascertain which wire is which and which battery they go to, and how to tell which one goes to the plus and which one goes to the minus. So it took me a couple paragraphs to describe the procedure for figuring that out. And then finally, like I tend to do these days on these schematics, is I have a little brief theory of operation for each of the functions. So for DC volts, I pick one of the voltage ranges and then put the components here and leave out all the switching, basically, so you can just see the important parts of the circuit. And then I have a couple of notes about how to do the math on it to verify and illustrate how the circuit works. And then I did the same thing for AC volts, but because I don't know the meter damping and I don't know the exact type of rectifier, that would skew any calculations I do and therefore not be very useful to illustrate the theory. So I just put a note about that and say, the theory is basically the same as with DC volts, that you add the rectifier, and also the meter needs a shunt in that situation. And because we don't know the characteristics of these or the damping characteristics of the meter movement, it's hard to figure out exactly how that is supposed to work, mathematically speaking. And then for DC amps, I did the same thing, some notes about it, and ohms, same thing. So that's pretty much the schematic. So let's just run through the simple theory for each one of these things. I'll just basically read aloud what my notes say. So let's say we're in the 50 volt DC range. So here's the plus and minus terminals. You apply 50 volts DC to it. Here are the resistors which end up in the circuit when you're in that range. And the meter movement itself is 2K or 2000 ohm value. And it's going to respond with a full scale reading to a current of 50 microamps. So if you add up all the resistances, it ends up being 1 meg. If you apply 50 volts across a 1 meg resistor, you get 50 microamps. And since it's a simple series circuit, 50 microamps flows in every part of it, including the meter movement. Therefore, the meter will give a full scale reading. And in the 50 volt range, the full scale reading is a 50. So that works out very simply and easily. I already explained that I didn't do the math on the AC volts. For DC current, and I should re-emphasize that this meter doesn't have the provision for putting a rectifier into the amp measuring or current measuring function, so it can only measure DC amps. We're going to use 100 microamps or the 100 microamp range in this example. So I have that illustrated up here. And the meter movement ends up being put in series with a 3K resistor. So the meter's 2K plus the 3K gives you 5K in this branch. Then the other 4 resistors in the current shunt, the 49, 50, the 45, the 4, and the 1, get put in series. 1 plus 4 is 5, plus 45 is 50, plus 4950 is 5,000, so I have 5K marked here. So then we do the parallel resistance formula. The 5K here and the 5K here comes out to a parallel resistance of 2.5K. Then we take the current for the full scale reading, 100 microamps, and multiply that by the 5K or the 2.5K that this all adds up to, and we get 0.25 volts across this whole thing. Then we divide the 0.25 volts across this by just one of the resistors, the one we're interested in. That's the resistance of the meter branch, the one that the meter is in other words. So that's 5K, so 0.25 volts divided by 5K gives you 50 microamps going through this branch or this path. Therefore the meter has 50 microamps going through it. Therefore it gives a full scale deflection, which on the scale of the meter is marked as 100 microamps, which is what we're putting through it. And then when you change to different current ranges, we take, for example, this resistor here and put it in this path or this branch. So then we would have 4950 plus 3K plus 2K over here, and on this side we'd only have 50 ohms because we'd have the 1, the 4, and the 45, and we would do the parallel resistances, calculate the new voltage drop for whatever maximum current we're putting through here, and then take that voltage drop and divide it by the resistance in the meter branch or path, and then we would know the current through this path and see how it deflects the meter. And then for the ohms, a common approach for analyzing ohm meter circuits of this vintage and this type is to first analyze the circuit with the resistor under test, which is called Rx. We analyze it as if it's a short circuit or 0 ohms, so we're only looking at these resistors. And then once we figure that out and verify that makes sense, then we try a half scale value of resistance out here and do the math and see if the meter will point in the correct direction to get a half scale value on the ohms scale of the meter. So what do we have here? We have we're going with the R times 1 scale, so the meter scale will be direct reading. We end up with a 1138 ohm resistor, a 21.85K resistor. The 0 ohms adjustment pot is a 10K pot, and we always assume that it's nominally set to midpoint, so we can think of it as a 5K resistor. Then we have the 2K resistance of the meter movement. And then you have this 11.5 ohm shunt over here. If we do the parallel resistance formula on that, the resistance ends up being 11.49 ohms. Then if we divide, that means the 1.5 volts from the battery is across this 11.49 ohm resistor, and that equals 130.5 milliamps, which I've indicated up here, 135.5 milliamps, assuming Rx equals 0. And then we do the ratio of this branch and this branch. So 11.5 ohms divided by 29988 ohms, which is what all these things add up to, equals that ratio, 0.00038. If we multiply the 135.5 milliamps by that ratio, we get 50 microamps flowing in this branch. The majority of the current is flowing this way, and just a little bit of it's flowing this way, and it turns out to be, it's not exactly 50 microamps, it's really close, 49,999 or something microamps, certainly close enough. And so that'll make this meter give a full scale reading, which we know will be a 0 on the ohm scale, and that corresponds to our Rx equal 0. Now we reanalyze it, assuming, looking at the meter scale, we see that the middle is approximately 12.5, not exactly, but close enough for this math, 12.5 ohms. All other assumptions are the same. Calculate a new total resistance, figure out the new current will be 62.5 milliamps instead of 130.5. And there's a certain amount of rounding off here. It's really got a lot more decimal points. It's the same ratio between the two branches, so we multiply the 62.5 milliamps by the ratio. We end up with somewhere in the ballpark of 24 microamps through the meter, which is an approximately half-scale reading, and the 12.5 is pretty close to that on the meter, so that makes sense. And then I just have a note here about when you change to the other ranges, What's essentially happening is some of this resistance gets removed from this branch and put over here. So less current flows here and more current flows here. And also the note says that when you get into the R times 10K range, you need to have more voltage drop in order to achieve the necessary current. So it adds the additional 6 volts made up of the 2 battery packs, ending up with a 7.5 volt total power supply for the circuit, and then you do the same math and it works out.